Hello, I'd like to welcome everybody to our Research to Practice webinar series on addressing non-point source pollution in Ohio. Funding for this series is provided in part by a grant from the Ohio Environmental Protection Agency. I'm Ann Baird, Extension Educator with the School of Environment and Natural Resources on the Columbus campus of The Ohio State University. Brian Weaver will be assisting me today. If you have any technical difficulties once you're logged in or even before, you can call or email Brian. On the right-hand side of your screen is a chat box, and you'll see Brian's, both his email and his phone number are in there if you do need to get a hold of him during the program. We'll be wrapping up our lunchtime webinar series next month on February 17th with Promoting and Protecting Ecosystem Services. You'll be receiving an email on how to register for that next week, as well as the link to the archive of the previous webinars in the series. Just as a reminder, again, you can view these at any time. They'll be posted and archived on the Ohio Watershed Network website. Throughout the webinar today, if you have questions or comments you'd like to share, either with me directly or all the participants, you can do so in the chat box on the right-hand side of the screen. There's a place where you can enter your comments and a drop-down menu. The default will go to me, the host, but you can also send them to particular participants today or all participants. And again, we'd like to take questions throughout the presentations, and we'll leave time at the end to get some of those answered. So please feel free to post those at any time. Without further delay, I'd like to introduce our first speaker, Bill Lynch. Bill is an aquatic program specialist with Ohio State University Extension. Bill is also housed here in the School of Environment and Natural Resources. Bill's principal responsibilities are to develop and provide extension programming in the area of aquatic ecosystem management. So with that, we'll go ahead and have Brian switch slides and presenters to Bill. Just while Brian's getting us switched up for Bill to present, I just do want to point out the way this program works is it's an audio broadcast format, so participants can only respond or communicate with us through the chat function. So if you do have something you'd like to share, please do so through the chat box. Okay, Bill.
Good afternoon, folks. I'm going to spend a little bit of time here talking about what happened here in the last couple of years and give you some background and some reasons why and talk about what's causing some of these. Just a little bit of review first. Why all the concern? These harmful algal blooms and the cyanobacteria that cause them have the capability to produce algal toxins. These toxins, in some cases, can cause health problems for pets and humans, particularly if ingested. These are rare. Certainly when we've had major problems in the state, we haven't had a whole avalanche of health issues, but some people are, and pets are, very sensitive to these toxins. The kicker is that the presence of a harmful algal bloom does not necessarily mean that toxin is being released at that point. So to know whether that toxin is there or not, tests have to be done by a qualified lab. So what are cyanobacteria? Well, they were once called blue-green algae, and they were considered the most primitive algae, and they were the first that showed up as the planet developed. Now we really know them for what they really are. These are bacteria rather than algae, but they contain chlorophyll and therefore are capable of photosynthesizing their own food. Many are capable of fixing their own nitrogen from nitrogen gas above the air-water interface or even in the water itself. And that gives them a real competitive advantage over other algae under certain conditions. Most have the ability to vary their buoyancy, which allows them to locate themselves within the water column wherever they want, and that provides another major competitive advantage. So as you go about your daily activities and you wonder what cyanobacteria looks like, these blooms, when they're at their worst, really does look like green paint being thrown on the water, as you can see in some of the slides. Microcystis particular, which is a very common one inland in reservoirs and ponds and small lakes, is very green. In the worst case scenarios, it's not unusual to see a very white foaminess or turquoise-colored surface material like you see in the one photo there in the middle. I will say that when I've come across a situation where I see that white foaminess and the blue-green or turquoise-colored, the toxins are always being released there. I've never run into that where there wasn't toxins in the water via lab testing. We do have mat-forming cyanobacteria in Ohio called Ligmia. It's in that lower left photo there. Very common in Ohio ponds and small lakes. It does show up in some of the reservoirs. We're fairly fortunate that this is not one. It can produce toxins, but it's not one that often does. So the question becomes, have harmful algal blooms in Ohio increased? And if you look at the 2009 map there, shows that we had 4, in the larger systems, reservoirs and lakes, we had 4 documented outbreaks. And here comes 2010, and it exploded. And, of course, the press got a hold of that, and we all got to read a lot of those articles. My first reaction was, oh, my gosh, we have this stuff all over the place. What's going on? So I took a road trip. I went and visited nearly all of these reservoirs and larger lakes to see what was going on, just to see if we were as bad as Western Lake Erie or Grand Lake St. Mary's. And in reality, when I went and visited these lakes, particularly in eastern Ohio, I really had to work to find the blue-green algae blooms, the cyanobacteria blooms. They were not large blooms. They were small scale. I hate to use the word minor because that implies that it's not very important, but they were there, but I had to look for them. They were typically in the headwaters of those reservoirs. The question then became, for me, was, okay, these are not major blooms in these other water bodies. What are the toxins like? Are the toxins there but in small amounts, or are they actually over the World Health Organization's thresholds? So I went back and got data from the Ohio EPA, and in reality, if you look at it, very few of these had microcystin levels above 20 parts per billion. As you can see, the smaller 2010 state map there to the left, which I showed you just previously, and then you look at how few are still present on the map to the right when we just look at those with high levels of microcystin. So, and to point out that nearly all were less than 1 part per billion, which is the World Health Organization's drinking water standard. So not only did we have small-scale blooms in most of these reservoirs, but the toxins, microcystin toxins, were not very high. So that begs the question as to why we're posting warnings for waters with low microcystin levels, because all those reservoirs had health advisories posted on them. Well, a lot of these reservoirs and larger lakes also had very low levels of anatoxin and saxitoxin, which are 2 other toxins that cyanobacteria can produce. The World Health Organization has not defined contact and drinking water standards for those toxins, those 2 toxins. And at the same time, research has indicated that they are likely more detrimental to human health and at low levels. So a lot of agencies across the United States, when they see anatoxin and saxitoxin at any level, will go ahead and issue a warning or place a use advisory for that body of water. And it's basically the better safe than sorry strategy. And I can't blame them at that point because we really don't know the long-term health effects of anatoxin and saxitoxin. Of course, I've got a lot of calls in the last year from newspapers and media. And they want to know, are they new to Ohio waters? No, cyanobacteria have been in Ohio from the very beginning. They are not a recent invasive from a distant global location like a lot of people hope for whatever reason. I guess it's a convenient excuse. Nor are they recent mutations capable of causing problems. Simply, they remain at low densities. They're present in all Ohio waters, but they remain at low densities until ecological conditions are created that allow them to reproduce quickly and then create these dense blooms. So the question becomes, what are these favorable ecological conditions? First and foremost, development of HABs is indicative of elevated nutrients, particularly in excess of phosphorus. the nitrogen to phosphorus ratios are important, and I'll talk a little bit more about that in a minute, but when the ratios are greater than 20 to 1, 20 parts of nitrogen for each part of phosphorus, we typically don't have HABs. We have the planktonic algae that drive the food chain for fish. We get less than 10 to 1, we certainly start to see a greater incidence of harmful algal blooms. I often get the question about water temperature because we did have a hot summer. Hot water temperature or high water temperatures in of itself does not cause harmful algal blooms, but can certainly cause minor blooms or small-scale blooms in waters with slightly elevated nutrient levels. So temperature does play a role, and we will talk a little bit more about that in a minute. Just a little bit more on these ratios. I like these ratios. It's easy to work with clients that I do. They can understand it. It's easy to test for. But when you have N to P ratios that are larger than 31, and certainly 20 to 1 is acceptable, you get the good algae, as I mentioned before, the ones that drive the food chain for baby fish and then grow game fish that everybody wants to go fishing for. Between 10 to 1 and 20 to 1, we can get cyanobacteria blooms, particularly in hot summers. And certainly I think a lot of reservoirs fit into that category this past summer. Get less than 10 to 1, the incidence of these HABs will go up quickly, particularly in nitrogen-limiting systems. Again, remember that many of these species can fix their own nitrogen, so that gives them a big advantage when there's a lot of phosphorus around. And then in some cases when we see an N to P ratios less than 3 to 1, it's almost a guarantee that there will be a bloom. I want to show you the Grand Lake St. Mary's example from this past summer. Of course, everybody's familiar with that probably. It's been in all of the newspapers. But if you look at the data, first of all, the nitrogen to phosphorus ratio data from the EPA, and I thank the Ohio EPA for providing this data to all of us. During the spring, from 4/15 through 6/9, our nitrogen to phosphorus ratios were quite high. To dates were in excess of 50 to 1. And that's good. There were no harmful algal blooms at that point. Before they could collect another data or another sample, we started to see toxins show up in late June, and the toxin levels went up very, very quickly. On 7/14, the Ohio EPA collected another set of water samples from Grand Lake, and as you might imagine, and thereafter, you can look at these nitrogen to phosphorus ratios, and they're very, very low, 10 to 1, and indeed, if you looked at the individual data points, because these are averages, there were numerous locations that were 4 and 5 to 1. So it was not surprising that given that dramatic decrease in N to P ratios that we were going to have problems. And that's the sharpest drop I've ever seen in my career, to go from 50 to 1 to 10 to 1 in the space of essentially a month. Well, there's two ways that the nitrogen to phosphorus ratios can go down like that. One is that phosphorus increases, or the other one is that nitrogen decreases quickly, or some combination. So if you look at the data, if you look at phosphorus, we came into the spring and through the spring higher than we would like to be. The target is 34 parts per billion, and we were already higher than that. So that's no surprise given some of the phosphorus loadings that have been documented by Heidelberg College for Grand Lake St. Mary's. What caught me a little off guard was look how high it went, how quickly it rose in the summer. A dry summer with very little stream input, very little water flow from the streams. This is indicative of an internal cycling problem. So we not only have this external phosphorus coming into Grand Lake St. Mary's, but it really appears that we have a major internal nitrogen cycling problem. I'll talk a little bit more about that in a few minutes. If you look at nitrogen really probably is largely responsible for that nitrogen to phosphorus ratio going down because after 6/9, the nitrogen levels just plummeted in the lake. This is probably indicative of the rain stopping about that time, and so we weren't getting any input of nitrogen from the external or from the watershed. And so nitrogen just plummeted as algae started to proliferate. Just to move on here, summer water temperatures do play a role. I was asked at one time to generate kind of a summary of how this water temperatures and nitrogen to phosphorus ratios interact. So that's what these next series of tables will show. When you have a high nitrogen to phosphorus ratio in excess of 20 to 1, 30 to 1, the good scenario, it's rare to have harmful algal blooms regardless of what the water temperature is doing. We had a very, very warm summer in 2010. Water temperatures in most water bodies was greater than 80, yet we only had a limited number of blooms, and most of those were relatively small scale. If we go to the next level of N to P ratios, that 10 to 20 range, 10 to 1, 20 to 1, the moderate, as I call it here, in cooler water, you're not going to have harmful algal blooms. As the water warms up, they're still relatively rare, but when you get above 80 degrees Fahrenheit in reservoirs and lakes and ponds, you can begin to have what I would term as small-scale harmful algal blooms. Again, small scale can still release toxins, and we may still have to issue an advisory, but these are not where the whole lake or reservoir is covered in green, for example. If we move on to the worst-case scenario where we have very low nitrogen to phosphorus ratios, 10 to 1 or less, in cool water, below 74 degrees Fahrenheit roughly, HABs are still pretty rare. Be honest with you, cyanobacteria are really favorite of warmer water. In cooler water, they're starting to come on, but they're not real happy yet. But look what happens as we go above 74 to 80. They start to become common, and that's why Grand Lake St. Mary's had a problem even in 2009 when it was a relatively cool summer. You look at greater than 80 degrees Fahrenheit and at the low N to P ratios, and you're just going to have harmful algal blooms. That's just the way it's going to be. It's now their favorite ecological conditions, and hence we're going to have them. Let's talk about watersheds a little bit, sources of excessive nutrients. You look at a lake, and I didn't realize I almost inadvertently made one look like Grand Lake St. Mary's here. That was a freehand drawing. But everybody, the red arrows indicate external loading, and a lot of people perceive that as the sole culprit, and certainly you see that in the newspapers and everything. Everything is based on what's coming off the land. You have to realize, though, that there is a major internal source, too, and that is the black muck in the bottom of these lakes and reservoirs, and even Lake Erie to an extent. That black muck's high in phosphorus, and there are conditions that will cause it to be released, and that can really drive a cyanobacteria bloom. But the external does influence the internal in the sense that the internal loading doesn't become a major problem until you've had years and years of excessive external loadings, or if you've heard the term cultural eutrophication or excellent eutrophication. So lakes start out with a minimal amount of internal phosphorus cycling, but as they add more and more black mud, then the internal becomes a major player also. So we've got to keep those two in mind. So if we look at the internal sources of excessive phosphorus, it basically comes from the phosphorus being overladen with a layer of anoxic water. When there's no oxygen along the bottom of a water body that has a lot of black muck, the phosphorus will be released from that black muck and make its way up into the water column and begin to cause problems. This is a major source in small water bodies such as ponds and small lakes, but it really can happen in any lake that's stratified. And most lakes know how to stratify, meaning you have a warm layer on top of a cold layer. They don't mix. The cold layer loses its oxygen during the summer because of the black muck chewing it up. But even shallow lakes, like Grand Lake St. Mary's, which probably doesn't really stratify because it's only about 6 feet deep from throughout most of it, but you can get localized depletions in muck-laden bays and creek mouths that could release the phosphorus. And I've seen this at Indian Lake, for example, which doesn't have problems, but we've seen oxygen levels in the main lake very normal, and you get into the backwaters and it'll be 1 or 2 parts per million just because of the black muck. External sources in ponds and small lakes, which we haven't talked too much about. We did have a lot of small-scale blooms in ponds and lakes, over 200 this past summer. These are very small watersheds, and they allow local sources to have major effects. And what I mean by local sources is just something that's in that small watershed. So we look at things like the pet horse, lawn fertilizer, Canada geese, leaking septic systems, and even in aquaculture situations, feeding the fish. Most aquaculture facilities in Ohio this past year had some at least small-scale blue-green algae blooms. If you look at the larger systems, the large lakes and the reservoirs, these have very large watersheds that allow widespread sources from a number of areas but to accumulate and have major cumulative effects. And, of course, the two that everybody's worried about right now in Ohio is runoff from manure applied to fields in some of the watersheds, particularly Grand Lake, St. Mary's, but also agricultural fertilizer runoff. So those two, but that does not discount that there aren't some other secondary sources in these watersheds, such as septic systems and lawn fertilizers. But probably manure and agricultural fertilizer runoff are the two biggies in most of these watersheds. Some other important factors just to make you aware of that can determine whether you have a bloom or not or how bad is lake retention time, high retention times, which means the water's in that lake for a long time before it has a chance to go over the dam, is a major HAB concern if the water's high in phosphorus. And certainly Grand Lake St. Mary's, again, is indicative of this, is that you have a lake that doesn't turn over very quick. It can take several years, depending on rainfall, for a little molecule of water to come in one end and go out the other. Low retention times, you might think that brings a lot of phosphorus in, but we don't see a lot of HABs in low retention reservoirs or where they get a lot of flow through, because a lot of times those lakes tend to be turbid, off color, and that tends to inhibit production of harmful algal blooms. So I have seen reservoirs in Ohio, Delaware would be one, where we've seen N to P ratios down around 10 to 1, but we didn't have a bloom just because the water was very brownish in color, very little sunlight penetration. Aquatic vegetation community is an ally in terms of mitigating the presence of harmful algal blooms. If you've got a good, abundant, well-diverse plant and algae community, good algae community, you're much less likely to have a harmful algal bloom. And then certainly the intensity and timing of rainfall events. Wet springs followed by dry summers really are the worst-case scenario for HABs. We had that this past summer. Certainly the data from Heidelberg College is showing that a lot of the headaches with Grand Lake St. Mary's and even Western Lake Erie is related to a couple of major rainfall events during the spring. Just to keep a perspective as we finish up here, waters with high nutrient loadings and low N to P ratios are going to have harmful algal blooms probably even in cool summers, just due to their nitrogen limited and there's plenty of phosphorus around. Many of the blooms we saw in 2010 were small scale. In a lot of these reservoirs, they were localized to bays and headwater areas that had black muck, so it was probably just a very localized phosphorus release from low oxygen water over black muck. My guess is that if we have a cooler summer in 2011, a lot of the reservoirs that had blooms this past summer will not have them next summer. And given the lack of definitive science-based data on anatoxin and saxitoxin toxicity, we're going to see warnings continue to be posted on state lakes, whether it's in Ohio or other states, for the foreseeable future. Again, it's that better safe than sorry strategy. Some final thoughts here. Harmful algal blooms in ponds and small lakes are relatively easy to correct. We have a lot of success with that with bottom aeration systems. Land use adjustments, for example, if the pet horse is causing the problem, we've got to make sure the pet horse lives where the water from his paddock won't get into the pond. Algicides can be used if done correctly, and alum treatments. You've probably all read about alum treatments to remove phosphorus from the water column. It does work, and we can turn around a small system pretty quickly. In large lakes and reservoirs, this is more difficult to correct and really requires major changes in watershed management and adoption of BMPs, agricultural BMPs. Quick fixes are costly and fleeting, given that the external sources of nutrients are constantly entering the water body. And what I mean by that, quick fixes, is we go in and we treat a lake or a reservoir with alum or an algicide, and we can knock out the phosphorus or knock out the algae. But almost immediately, the phosphorus levels are rebounding relatively quickly. And so it's hard to get a long-term improvement in a water body if the external sources are continuing to hammer at it. And I'll just final thought as I end here is I often get the question that if we can turn off the external phosphorus loading from the watershed, won't the reservoir improve quickly? Given in the case of Grand Lake St. Mary's, if we could turn off the phosphorus loadings today and not have any for years and years, yes, the lake will improve, but it'll be very slow because of all that internal phosphorus cycling. We've literally got to work our way through that, and so it may take. I've heard estimates from limnologists 15 to 20 years for Grand Lake St. Mary's to improve just from turning off the external phosphorus cyclings. So this is something you have to be patient with, and that's why a lot of groups are looking at, okay, we need to do something in the lake too, whether it be removing the black muck or treating with alum. So I just want to make that point is that lakes can heal themselves, aquatic ecosystems can heal themselves, but you have to be patient if you're just relying on turning off the external loadings. With that, I'm done.
Thanks very much, Bill. Just a quick note, Bill's email is in the chat box, and that we'll also have time at the end to take questions that have already been submitted for Bill, but if you don't get them all in, please feel free to email them after the webinar. I'd like now to move on to introduce our next presenter, Jim Horman. Jim is a county extension educator with Ohio State University Extension in Mercer County, Ohio. Mercer County has the highest gross livestock receipts in Ohio and also has nutrient runoff problems and associated toxic algal blooms in Grand Lake St. Mary's. Jim is working on his PhD in environmental sciences, and his research is looking at the use of cover crops and no-till to recycle soil and manure nutrients to improve soil productivity and structure. So with that, I think we've got Jim loaded up on the screen, so we'll go ahead and turn it over to him.
Good afternoon. Yes, we're going to talk a little bit about the Grand Lake watershed, and we'll talk about some of the things that are going on with some of the manure regulations, and also just a little bit about how we're trying to deal with some of those problems. So first, I'd like to start off with a lot of what we're dealing with is soil ecology, and basically what soil ecology is it's basically how plants, animals, microbes, and humans interact with the soil. So that's what we're going to be talking about in this presentation. So if we look at healthy soils versus sick soils, basically healthy soils have these things in common. A key component is live plants growing year-round to absorb the energy and the nutrients. And a part of that is also having healthy microbial populations because these microbes process 90% of the energy in the soil. If you look at our land right now, typically when we plant crops in a corn-soybean rotation, we only have live crops out there from about May through September. And so we're not getting as much energy into the soil, and it's having a big impact on these microbial populations. So we say there's anywhere from 1,000 to 2,000 times more microbes associated with live plants. And microbes are very important for keeping both nitrogen and phosphorus recycling in the soil. Sick soils have these things in common. They tend to be compacted. They have high bulk density, poor water infiltration, and they tend to be bare. They're very low in soil organic matter, and we tend to get nutrient imbalances. One of the things that's happened through tillage is that we've lost about 40 to 60% of our soil organic matter over the last 100 to 150 years. And the reason that's important is every 1% organic matter holds about 1,000 pounds of nitrogen and about 100 pounds of phosphorus. One of the things that we're starting to talk about is how we can mimic Mother Nature, especially in our manure management. And here's just kind of an analogy. We used to have 60 million buffalo in the United States, plus all the other animals, the antelope, the deer. They basically grazed and deposited their manure year-round. And as far as we know, the water quality was excellent. So here's a question. Did those animals stop grazing and pooping during the wintertime? And basically the answer is no, they didn't. So what we need to do is take a lesson from the buffalo and Mother Nature. If we keep the soil covered year-round, we'll keep those plants growing and we'll keep those active roots, we can tie up a lot of nitrogen and phosphorus, and we need to spread that manure thin to fertilize our crops. The result will be clean water and healthy, productive soils. Keeping the land green keeps the water clean. So that's something that we're really starting to emphasize. And here's an example here that shows what happens when you overgraze. Or you could even relate this back to some of our lawns and to our golf courses. We say that about 50% of the vegetation is above ground and 50% below ground. And depending on how you manage that vegetation, that's how many roots you're going to get. So the shorter you keep your plants, the less roots you have, and the less live roots we have, the more nitrogen and phosphorus can be lost from that watershed. Let's talk just briefly about nitrogen storage. We have two forms of nitrogen. The inorganic forms, basically what's in our chemical fertilizers, is a very fast release. It's in two forms, either nitrates and ammonia. Now, clay soils have a negative charge, so it will hold on to that ammonia because it has a positive charge. But the problem in the soil is that ammonia and nitrates go back and forth. They're very easily converted back and forth. About a little, maybe just a little bit greater than 10% of the nitrogen in the soil is in this inorganic form. Organic forms, however, are a slow release, and when you think about nitrogen this way, you're thinking about amino acids, proteins, nitrogen, and sulfur. And so this form of nitrogen is stored in the microbes, the plants, and the crop residue, and also that soil organic matter. It makes up the largest part of the soil. However, we've lost a lot of that. As I've said, we've lost 60 to 70%. So if we can increase the amount of organic forms of nitrogen, it'll be a slow release, and we won't have near as many problems with nutrient runoff. Here's just a quick slide showing nitrogen recycling, some of the ways that it's lost. On bare soils where we're conventionally tillage, we're worried about volatilization, but typically where we have the land covered, we don't have as much problem with volatilization because the organic matter will help to moderate both temperature, moisture, and the nutrients that are released. One of the big areas that we're losing a lot of our nitrogen is through leaching and soil erosion. You have to remember every 1% soil organic matter has that 1,000 pounds of nitrogen and phosphorus. The soil organic matter is light, and so it tends to float off. So when we get soil erosion and sedimentation, we're losing the most productive part of our soils. Another big area that we're seeing losses is denitrification on our heavy clay soils. We could be losing as much as 40 to 60% of our nitrogen from denitrification when we have standing water here in the spring. Just taking a look at soil versus water P levels. Good soil to grow good crops, we need about 25 to 50 parts per million of soil phosphorus. That's about 50 to 100 pounds per acre if we're growing corn, soybeans, and hay crops. A high soil P would be somewhere around 75 parts per million or 150 pounds. At these levels, we're really starting to lose a lot of the phosphorus because it's not being tied up. And we've got some that are extremely high where we get above 150 parts per million or 300 pounds per acre. In this watershed, we've had a lot of poultry, and in some cases, we're approaching well over 1,000 to 2,000 pounds of phosphorus per acre. So that is a concern in that area. Well, what's good for the soil isn't always what's good for the water. Good phosphorus for the water is about 10 to 50 times less. A key component here is that our land-to-water ratio, we've got about 4 to 5 times the number of acres that we do water, so just a little bit of phosphorus leaching out of those soils or as sedimentation can cause a huge problem in a shallow lake. And that's the other key thing is we have a very shallow lake. It's on average about 5 to 6 feet deep. The average retention time is about 1 to 2 years. However, one thing that has changed is we don't know how much of that water is going over the dam. A lot of that water could be staying there, and so it's not all being left out. And again, Bill talked a little bit about the cycling of that and how long that phosphorus can last in the lake. Here's a graph that shows, slide that shows a little bit about phosphorus. Our current phosphorus efficiency is around 50%. Somewhere around 50 to 75% of the available phosphorus is in the organic form. What's interesting is that the organic matter helps to form a bridge to the clay. And so you'll see this clay particle here that's orange. We've got a phosphorus ion in between there, and we've got the organic matter. Well, as we lose organic matter and we have less organic matter in our soil, you notice that phosphorus now becomes exposed, and so it can basically disassociate and become more available. So if we can increase the amount of organic matter in the soil, we can help to keep that phosphorus tied up. How much nitrogen and phosphorus is allowed in the water? Basically, the EPA has come out with a standard. They're saying 1 milligram per liter or 1 part per million. On phosphorus, it's 10 times lower. It's 1/10 of a milligram per liter or 1/10 of a part per million. So how much can we lose per acre? Well, we looked at our TMDL here for Chickasaw Creek, and 1 part per million on nitrogen is less than 2 pounds of nitrogen per acre. That's not very much nitrogen when you consider how much manure and fertilizer that we're putting out there. It's even worse for phosphorus. The phosphorus numbers are around 0.1 parts per million, which is 2/10 of a pound of phosphorus per acre. Here's some numbers for the Chickasaw Creek just to give you an idea where we're at. Currently, our allowable is 0.2. We're currently losing about 1.67 pounds of phosphorus per acre. That's 88 times more than what we should have. For nitrate, again, we want to be less than 2 pounds per acre. We're currently losing about 40.8 pounds, which is 20 times over what we would like to see. But we have seen some water quality improvement in the Chickasaw Creek. If you look at what our TMDL says, how much we can lose, it's right around a ton, a little bit less than a ton, and for nitrates about 12.1. If we look at 2007 through 2008, we were losing 14.7 and 534 tons of respectively of the phosphorus and the nitrate. We actually saw some improvement. You can see that we've reduced that by 40%. We still need to get rid of about or reduce the total phosphorus by about 60% and the nitrates by 40%. But we are making some improvement. One of the problems, though, that we have is with soil compaction in our watershed. And here's a visual way that you can look at the soil compaction. We're actually seeing that with our fence rows, we're seeing about a 6 to 9 inch elevation difference. That's what's occurring. Our soils now have actually shrunk, so that means they have less room for air and water movement. And the reason that's becoming a problem is that when we have compacted soils, the iron tends to be released, and it's the iron and aluminum that's tying up the phosphorus. So we're seeing extremely high levels of soluble iron in some of our soils, and we're seeing a lot of standing water, which indicates that we have a compaction problem. We also did some calculations here, and basically if you want to compare conventional versus no-till, is it possible that we can reach these standards? Well, if you look at rainfall intensity, as Bill talked about, we lose most of our nitrogen phosphorus when we have a very extremely high rainfall event, say 4 to 5 inches. And if you take these all into account, basically with conventional tillage, we could be losing as much as 13 pounds of phosphorus lost per acre. If we adopt a system that has no-till and cover crop, which very closely mimics the Mother Nature, with this same rainfall, we're getting much better infiltration. We have the phosphorus is being retained in the soil. We can actually meet the standard. We're at 0.06 pounds of phosphorus lost per acre. So it is possible to meet the standards, but it does require some changes in management. Here's some data on what's happening in Chickasaw Creek, how much rainfall is occurring, and you'll see that actually the worst months for rainfall is April, May, and June. We do get some during the wintertime, but we do have conditions during the wintertime where actually it might be beneficial to be applying manure. So we're looking at some ways that maybe we could still apply manure in the winter. Starting in 2012, there will be a total ban on manure application from December 15th through March 1st. Here's what we're looking at. What we're looking at is, we've probably read in the news or you've seen articles that says that no-till is bad, earthworms are bad. And basically on the right we have a no-till situation or an earthworm hole, And basically what's happening is here in that top layer, we're getting a lot of nutrients, and because we've created this macropore, a lot of those nutrients can very easily be flushed out of the system and go down to the tile. When we add a crop, no-till with the cover crop, those nutrients are recycled within that. So plants act like a biological valve to help absorb that nitrogen and phosphorus. And again, keeping the soil green will help to keep that water clean. Here's basically how we can help to save nutrients in the soil. It's related to the speed of water. If you double the velocity of water, how many more nutrients travel in that stream with the water? It's basically exponential. It goes up 2 to the 6. So if we were to increase the speed of water in a stream from 1 to 2 miles per hour, we have 64 times more nutrients that can be transported off. And as you go down there, you can see we get up to, if we go from 1 to 32 miles per hour or 1 to 16, it's 512 to over 1,000 times more nutrients. One of the benefits of having no-till and a cover crops is that it slows the water down. It forces the nutrients to drop its load in the soil so that the plants can absorb it. So no-till with cover crops helps to take care of part of this problem. And here's basically what we're looking at. We've gotten away from some of these natural cycles. Natural vegetation and no-till and a cover crop are here in green. We have a steady state. When we have this, when we do conventional tillage, we disrupt a lot of these natural cycles. We get soil compaction, and a lot of the nutrients are lost. You have to remember, when we do tillage in the fall, the microbial population really expands. They absorb a lot of this nitrogen and phosphorus, and then as they die off in the wintertime, a lot of that nitrogen and phosphorus is released in the spring, and that's when we're seeing it show up in the streams. Here's just a quick picture that shows the impact of sedimentation. We have conventional tilled fields on the left that have this brownish colored water, no-till fields, and if we can keep a crop there, we have clear runoff from the no-till fields, and it shows the impact of what's going on with those disturbed aggregates. We're really trying to get more macro aggregates from live crops out there that will tie up both nitrogen and phosphorus. Here's another picture, shows the same thing. Basically, where we're cropping with annual tillage, 2% in the top 4 inches. If we can increase that organic matter, we can start to tie up both the nutrients and keep our water a little cleaner. Here shows what the roots do, how they help to expand the soil. Basically, they're forcing their way down, and they actually compact the soil, but they also improve the soil structure. It gives us more room for air and water, and it helps to tie up the nitrogen and the phosphorus. So as we look at some of the cover crops for winter manure, if we were to apply manure in the winter, what do we want in a good cover crop? We need to have live plants. We need fibrous root systems, are much better than a taproot. We need something that will hold up the equipment, something maybe we can use for forage, something that's easy to kill, and also we don't want problems for the next crop in the way of insects, weeds, or nutrients. So which cover crops are we going to use? We're looking now at using grasses that have a live root. Grasses do a very efficient job of tying up both nitrogen and phosphorus, and they don't make more nitrogen. They live year-round. We are not recommending oats. They do help to provide some traction. We can hay and graze them, and they are fairly easy to kill, and we don't have too many problems with some of the insects and some of the other things. Now, seed-to-N ratio can be an issue, but we're finding ways to deal with that by killing it early. And so here's what we're recommending. Cover crops for winter manure. The good cover crops would be cereal rye, wheat, triticale, annual ryegrass, spelts, and barley. We're not recommending the oilseed radish because they don't live throughout the winter, nor do the oats. Legumes are not recommended because they have a taproot. Hay fields, we've had some problems with preferential flow. That's manure getting down into tile lines through the macropores. And we're not recommending the short pastures because they don't have enough roots to absorb the nutrients. So in summary, we're basically looking at N losses around 1 milligram per liter, and that would be 1 part per million. We need to get this down to less than 2 pounds of N per acre. P losses, we have to be 10 times lower than that, 0.2 of a pound of phosphorus per acre. We're working with using active live roots and the microbes to work together to improve the soil structure, and we're looking at winter annual grasses are good for manure application to help absorb that N and P. So that pretty much concludes my talk. Thank you for your time.
Excuse me. Thanks, Jim. I want to thank both of our speakers. We'd like to open it up for questions now, and several people have sent some. And if you have more during this part of the program, please just go ahead and send them, and we'll try to get them in. I'd like to start with some questions for Bill about his talk. We've got a couple chemistry type of questions. Someone wondered if there was any water testing in addition to HABs, also for atrazine or other chemicals associated with pesticides and fertilizers. In addition, are nitrogen and phosphorus measured as total P and total N, or as another form such as nitrate and phosphate?
Well, let me answer the last one part first. We do total nitrogen and total phosphorus because of the ease of the testing and how quickly we can get the results, and they are very good predictors of the appearance of harmful algal blooms. I will freely admit that there are subcomponents of that are more critical to the growth of the harmful algal blooms than just total N and total P. Nitrate, for example, on algae, that's the one that grows algae quickly or is good for algae. But there are other forms of N that don't provide that. I'm not aware of any testing in Grand Lake St. Mary's or anywhere else where they're pairing up atrazine or other chemicals in addition to water quality testing. Okay. Algae would have to answer that.
Okay. Thanks, Bill. I'll switch over to Jim now. Jim, we had a question. Have you reached out to landowners/farmers to encourage to adopt practices such as cover crops? And if so, what has been the response?
We've had quite a response here. Right now, farmers are getting paid $50 to $70 per acre to put out the cover crops. One of the things that we're working with is we're working with EPA now and the Ohio Department of Agriculture to maybe encourage the use of cover crops along with winter manure applications. There may be some exceptions, and the exception may be that if you have a good grass cover crop, we may allow you to put on 5,000 gallons of liquid manure per acre. That is less than 0.2 of an inch of rainfall. So if a farmer had 100 acres, they could actually put out almost 500,000 gallons of liquid manure out there. So that is one way that I think that we can actually help to solve this problem, because I actually think that the biggest problem that we have in this watershed may not be manure. It may be soil compaction. Our soils are so dense, and we're getting those saturated soil conditions that's freeing up the phosphorus. And then if we do any kind of tillage, we're getting a lot of sedimentation into the lake. And so we got to keep it covered year-round. Farmers are interested in that. They're still learning. Hopefully we can increase the adoption. But we've got probably at least 5,000 to 6,000 acres of cover crops out this year, and it's going up every year.
Okay, I'm going to switch back to Bill. One mitigation demo project looked at shifting algal populations from blue-green to diatoms through the addition of silica. Could you talk about some of the possibilities of this type of population change?
Yeah, they tried that I think in one or two of the bays up there. And diatoms, look, Grand Lake St. Mary's has diatoms. There's no doubt about it. They're found everywhere. But diatoms are a cool water species. They predominate in the early spring and late in the fall. That's the normal time they show up. So I'm not sure that silica is going to do much for us in the summer during the heat when the diatoms naturally die back anyway. But I have not seen the outcome of that experiment yet.
Okay. This is just a kind of a basic science question. It looks like a lot of N and a little P is better than the reverse, and I think someone just wanted just a short clarification on that.
Okay. Well, a lot of N and we don't want a lot of N. I mean, that will cause other problems. If you have a pond with filamentous algae or other things, even planktonic green algae, the ones that drive our food chain, the good planktonic algae, can get out of hand, and that would be caused by an excessive amount of N. Where we get in trouble is when we have a lot of phosphorus in relation to what N we have, and so we don't want to get astronomical nitrogen levels in any system. I mean, even if we don't have the cyanobacteria bloom, we could have other headaches.
And I might just add to that, we're not looking at adding nitrogen or ammonia to the lake. I think we've said that before. That's not the solution. So that was what some people were thinking, I'm sure, but that's not part of the solution.
Okay.
Yeah, I would agree.
Shifting back to Jim again, will no-till farming be cost productive for the farmer in the short term, and could you address that also for the long term?
Yes, what we're seeing with higher fuel prices, with higher fertilizer prices, which is related to fuel, typically what we say is it takes 7 to 9 years to convert to no-till by itself. When you start getting the biology corrected by using cover crops, we can make that transition in 2 to 4. And if we add manure, we can actually do it in even less time. So we've got plenty of manure here. Our biggest issue is we've got to get rid of that soil compaction. We've got to get our soils looser, and we're not going to be able to do that with iron. Iron actually makes the soil worse, and I've got a whole presentation on that. I can't go into all the details, but the quick answer is, in the short term, we may need just a little help, say for a year or two, but after 2 years, 3, 4 years, we should be able to even outperform conventional till soils. So that's really the key to this is we just need to educate our farmers on how to do it and start helping them to make that transition.
Okay. I think this will be for Bill. Bill, someone asked, do you think on a shallow lake like Grand Lake St. Mary's that a lot of the recreational boaters stirring up muck is a contributing factor for the internal portion of the problem?
Every time I was around Grand Lake St. Mary's this past summer, there were no boaters. I'm not sure that had major bearing this year. No, what the boating will do as you run your prop through the muds and everything, it doesn't have much of an impact on the phosphorus per se, but what you do is when you resuspend that black muck very quickly, it gets up in the water column. It wants to go ahead. Black muck isn't fully decayed, and it wants to go ahead and decay real quickly, and it'll start using up quantities of oxygen pretty quickly. And so, for example, in the numerous canals around Grand Lake St. Mary's, where we have black muck buildup, we know we do. We also know we probably have low oxygen levels in there based on our experiences with Indian Lake. When those boaters are going in and out and resuspending that black muck, they're probably contributing to the depletion of oxygen in their little channel very, very quickly. And that would be more of a concern. I'm not sure there would be enough boaters there's so much black muck in Grand Lake St. Mary's that it would take just an army, a fleet of boats going back and forth all day.
And Bill, maybe you can mention some of the harmful fish, the carp and the bullheads, what effect that might have on them.
Well, that's a good point. When you get a lake that's that eutrophic, which I mean by high nutrients and phosphorus and stuff, it's just natural for the lake to become dominated by what some people will refer to as rough fish, carp, bullheads, things like that. And they will root along the bottom and can release some phosphorus. Again, if there's no oxygen along that mud, we know we're going to get a lot of phosphorus release. And if there's no oxygen along that mud or the first foot of water above the mud, then the fish aren't going to be down there doing much. I mean, they're not dumb. They're going to move away and go find oxygen. But certainly you can get some phosphorus release just the way, we call it macropore phosphorus in the upper layers of the mud if they're rooting around.
Okay. There was a question about the installation of constructed wetlands as an interceptor of nutrient runoff from fields. I wonder if maybe either one of you could speak to that question.
Well, I'll go first, and I'm sure maybe Jim can have some comments. Wetlands are kidneys. They filter out nutrients and contaminants. I will say that constructed wetlands never operate as efficiently as a natural wetland. So when you lose a natural wetland, you're really losing a lot. But the data I've seen, even with a wetland, if you're hammering the wetland with phosphorus, eventually its utility will start to decline. I mean, a wetland can only process so much phosphorus so quickly, and then you just overwhelm it. And so these big rain events, you may still get a fair amount of phosphorus going out the back end of that wetland if the wetland can't really handle the additional phosphorus. And also keep in mind, the wetland's at its best in warmer temperatures. So if you're getting a lot of phosphorus going through a wetland during cold periods of the year when biological activity is really reduced, you're probably not getting much phosphorus uptake.
Yeah, and I guess what I would say in addition to what he said is that cover crops and live plants on the soil on a field act the same way as what a wetland does. And the farmer, the benefit to the farmer is that he keeps the nutrients on the land. And so it just makes sense, I think, that when you start looking at our agricultural landscape, 80 to 90% of it is farmed, and generally it's bare. Now, in this particular watershed, we do have a lot of hay, so we may have as much as 20, 25% that actually is covered with wheat and hay, but if we could cover a much larger percentage of that, we could keep that nitrogen and phosphorus tied up. And, that's why we use basically waterways, filter strips, and buffers. All those have live plants in it. And if that's a good practice, we ought to be applying that to a much larger percentage of the field. And by doing that, we can do that with no-till and cover crops.
Okay. I think we're going to end with a couple of questions on the concept of dredging. The first dealt with the western Lake Erie Basin and was wondering if that was related, dredging there was related to impacting the algal bloom in that basin, last year's dredging.
The dredging that I'm aware of going on up there is the Toledo shipping channel and harbor, and they're taking that material out and they're going out into Lake Erie, western Lake Erie, and dumping it. I don't know of any dredging out in Lake Erie itself. It's up in the harbors and channel. Now, obviously, when you take that black muck and you go throw it out there, I mean, you're having an impact. But given the context or keeping things in perspective, that amount of material is being taken out probably contains far less phosphorus than the total coming off the watershed.
Okay, and then a question about black muck on the bottom, I guess, from the discussion on Grand Lake. Should that be dredged out eventually?
Grand Lake, if you could snap your fingers and make all the black muck disappear in Grand Lake real quickly, you would see a dramatic change. Now, we still got to deal with watershed issues and reducing P and nitrogen and whatever, because we'll come right back to the same spot. But I cannot come up with a scenario in my mind where we could get enough dredges that would run 24/7 to get the black muck out of there in a timely fashion. I just don't think that's possible. I'm not against dredging canals and channels and stuff for boaters and whatever, but I'm not sure that's a viable option to correct the lake very quickly.
Okay. I'm going to have to wrap up the question, and thanks to everybody who took the time to submit those. We really appreciate that. If you have other questions for Bill or Jim, we're going to leave their emails are up in the chat box now, and that'll be up for a while after the call ends, so you can copy and paste those. And we really want to thank everybody for participating and spending their lunch hour with us. We do have a really quick, about a 1-minute evaluation. It's the link to that is on our website, and it's posted now in the chat box where it says, please complete the evaluation. So if you take just a minute or two to do that now, that will really help us out for future webinars. And again, I hope everybody can join us on, I believe it's February 17th for our next webinar, Promoting and Protecting Ecosystem Services. And we'll look forward to seeing you all then. And with that, I want to hope everybody has a great day, and we're going to end the call now. So thank you. Thanks, Bill and Jim.
Thank you.
Okay.
You're welcome.
Bye-bye.